Pause the video, give this question a go yourself first. Okay, so this question is asking us basically how does an interpreter work? So we know that it works by examining, I can't spell examining, source code one line at a time, or one statement at a time. It checks each statement for errors. If yes, errors reported. Interpreter halts. Ramp stops. If no, statement is executed. We also know that for every iteration, so i.e. in loops, interpretation, so if we have like a for loop, we know that this will be interpreted, and it's going to be interpreted again and interpreted again, so the interpretation is repeated. And we know that the interpretation of doing this is repeated every time we hit run. Pause the video, give this question a go yourself first. Okay, apart from syntax analysis, two other stages. Well, you've got lexical analysis, we've got code generation, which I can't spell, and we've got code optimization. So lexical analysis is all about converting source code into tokens. This code generation is about producing object code, which again I can't spell. What is up with my spelling? And optimization is all about improving runtime and efficiency. Of object code. So we turn to object code first, which then allows us to optimize it, which enhances memory and runtime. Pause the video, give this question a go yourself first. Okay, this stage can improve the time taken to execute a statement. That would be optimizing our code. This stage produces object code. Well, we know that that's going to be at code generation when it does that. This stage makes use of tree data structures. We know that with that it's syntax analysis. And this stage enters symbols into a symbol table. Finally, that will be our lexical analysis. Pause the video, give this question a go yourself first. Okay, so we've done, after the syntax analysis stage, the compiler generates object code. The equivalent code in assembly language is shown below. After we've done code generation, what comes next? Well, that would be optimization. So code optimization, to remove anything which is not needed from our code because it's redundant. Pause the video, give this question a go yourself first. Okay, so we've got this statement. This stage removes any comments in the program source code. Well, that's lexical analysis. It gets rid of comments. This stage could be ignored. optimization. We don't need to do optimization, therefore it can be ignored. This stage checks a grammar. We know that grammar is for language rules, so syntax analysis, and producing tokens, we know it's lexical analysis. And this would be the order of how it runs: lexical analysis, then syntax, then code generation, then optimization. So this is our information, this is the question. Pause the video, give it a go yourself first. Okay, so we're doing lexical analysis. So let's begin. So we've got a symbol, start, 1, next thing is number, and within that, numbers could be 62 because it's sequential. There's a variable. In our next thing, it's counter, which will be 63, which is a variable. We've already got start in our table. 12 is our next symbol, which is going to be 64, and it's a constant. It's just going to be 12 the whole time. It's not going to change its value. So we're going to do the output from lexical analysis stage is stored in the following table. Each cell stores 1 byte of the output. Complete the output from lexical analysis stage. Use a keyword table and the sounds to do it. So we've got 60, 1. So the next thing we want to do is 61, which is that. Then input, which is 51. And then we've got number, which is 62. And then we've got our 4, which is 4E. We've then got 63, which is counter. The arrow again, which is 1. We then have 60, which is start. We then have 2, which is 50. We then have 12, which is 64. We then have 52, which is going to be our output. We have number, which is again 62. We then have 02 for the multiply, counter, which is 63, and 53, which is N4. Easy. Pause the video, give this question a go yourself first. In fact, there's several questions here. Good luck. Okay, 2 types of data in the keyword table, 2 types of data in the symbol table. Well, let's just have a reminder of both of these tables. We've got the keyword table at the top, which has things such as if, then, and if so, like reserved words being used. So I'm going to put that in here. We've also got operators in here like equals, asterisks. We also store the corresponding or matching tokens. All of these things are stored in the keyword table. In the symbol table, this is slightly different. We use identifier names, i.e. start. But we also have the type, i.e. constant or variable. Or actually, I'll call that for role rather than a type, even though it's type here. We also got the value of the identifier, i.e. 60 or 61. Which is actually its location. So it can be found. So the value location of the identifier. Explain how the contents of keyword and symbol tables are used to translate the source code. Well, step 1, basically this is asking us how you do this table, blah, 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 blah. So step 1, keywords and operators are looked up in a keyword table. These keywords have corresponding tokens. Identifiers are looked up in symbol table. We then convert to, well, we convert identifiers to their location value. So think back to the task where we had to put everything down below, like 61, 2, or 0, 2. I'm just making these numbers up. Then 60, blah, 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 blah. After that, we put it in sequence. Of tokens based on program, which is basically what we're doing here. One additional task which is not involving keyword or symbol table. So what else does lexical analysis do? Well, it gets rid of white space or comments removed. It could also get rid of redundant characters and identification of errors, but not necessarily syntax. Two tasks in syntax analysis. Well, it produces an error report, so we can do that as the first one. Another is check the table of tokens to ensure rules of grammar are obeyed. And finally, it constructs a parse tree, which is this. So it basically creates a template for what's allowed and what's not allowed when it comes to the rules. So in fact, this will be the first thing it would do. Create this parse tree, it will then check against the tokens and then create an error report if there's anything which is wrong with the tokens, which we've been given against the template, i.e. the parse tree. Pause the video, give this question a go yourself first. Okay, so we know that optimization minimizes the amount of RAM being used, but also, why else would we do that? Well, it shortens execution time of program. There we go. Pause the video, give this question a go yourself first. Okay, what I'm going to do is simply map this out. First thing we're going to do is load A to the accumulator. So A is in the ACC. We're then going to add value B to the accumulator and then store the accumulator in X, the result. So let's say 2 add 3, which will be 5. Excuse my coughing. It then tells us to load value A to the accumulator, but we've already got value A in the accumulator, so we don't need to do that. It's still there, A being 2. Add value B to the accumulator. Well, again, we've already got value B in the accumulator, so we don't need that. So we've still got 2 plus 3. add value C to the accumulator, which is not going to be, let's do give it 4. So we do need that. And store the results into Y, which would give us 9. It then tells us to load again to value A, not needed. We don't need to do add 237 because we've already got it. We don't need to do add 238 because we've already got it in the accumulator already. So now let's do D, which is, imagine it's 8. So we add it to the accumulator, store the results, so 12, 15, 17. Done. These numbers I've just made up, just if you get confused. So you just need to rewrite this without 1, 2, 3, 4, 5 lines. Pause the video, give this question a go yourself first. Okay, similar to the last question, let's play this through. Let's imagine this is 4, 2, 1. Reload value B into the accumulator, so that'll be 4. We then add the value C to it, which will be the 6. We then store results into, so 6 into address 567. We then load 567 and put it into the accumulator. But we've already got 4 plus 2 is 6 here, so we don't need to do that. We then add 236, which gives us 7, and we store it in 233. So the next question is, why did we have to do this? There's no point storing it into here if we're just going to add another number to it anyway. So that's 2 lines we didn't need. Okay, pause the video, give this question a go yourself first. Well, we're using, at the moment, we're going to be looking at syntax diagrams and BNF. BNF is basically used to help define programming languages. They're there to help us with, when we're using a compiler, to help us analyze the source code. That's what it's there for. For each one of these, we need to give a reason and then complete the BNF based on the diagrams you've got on the left hand side. So these are all invalid. Well, C4, and look, I'm saying C4 is not signed integer. It needs to be a signed integer in order for this assignment to work. Okay. The next one, which is, we've got an issue with 10. Not, so 10, I'm going to put not signed integer. So it needs to have a plus or minus sign behind it, but also we've got another issue with the 0. 0 is not a digit. Also, we've got 2 digits, only 1 digit is allowed. This next one, we've got a couple of issues. Number 1, 6 is not a digit. Number 2, for assigning, it's an equal sign, not for the assignment operator. And is there anything else an issue with this? Well, we've got the minus, so that's fine. Okay, now we're going to complete BNF for the syntax diagram. So an assignment statement. Let's do I'm going to actually work my way backwards from operator all the way to assignment statement. So an operator equals that or that. For the assigned integer, it equals, and I'm going to do a plus, and I'm going to write the words inside these brackets, digit, crocodile brackets, or minus digit. The or has to happen after the digit. For a variable has to be a letter, but actually 2 letters. An assignment statement has to be excuse me, variable equals variable operator and then signed integer. And finally, we write the BNF, so a variable can be any number of letters. To do that, we're going to put letter, and I'm going to do or, and I'm going to do, it doesn't matter which way around you do this next bit, letter, variable. So like saying adding on a letter to the variable already to make it grow. Okay, so again, this is a combination of BNF and syntax diagrams. Pause the video, give this a go yourself first. Alright, so what's the problem with this? Well, 5 by itself is not a variable. 5 is not a variable. A variable is made up of a letter and, so letter or an unsigned integer, which is multiple digits, or 1 digit. This next one, D is not a letter. This next one, it's got a variable, it's got equals, it's got a variable, it's got an operator, it's got a variable, but it's got multiple operators here, so that's an issue. So multiple operators not allowed. It's also got 3 variables. Well, it's got 3 variables after the equal sign. Now we're going to do the BNF. Alright. So let's start with the operator, that's the easiest one. We've got a plus, or a minus, or multiplication, or divide. We then got an unsigned integer, which is basically a digit. What am I doing? I can't write digit. Or digit unsigned integer. We then got a variable, which is made up of a letter or multiple letters. Sorry, not multiple letters, or an unsigned integer. And then we've got variable, which is made up of, sorry, assignment, which is made up of a variable. And then we've got an equal sign, and then we've got another variable. Then we've got an operator, and then we've got another variable, and then we've got a semicolon. And finally, the syntax of variable is changed to allow one or more letters followed by an unsigned. So we're just going to modify what we've got here. We've got variable, letter, unsigned, integer. But we can also have multiple letters. Pause the video, give us a go yourself first. Okay, so let's do it. We've got operator, I'm always starting at the bottom. That's just how I roll. We've got plus, we've then got minus, we've then got asterisk, we've then got little hat thing. We then have letter. Letter is made up of A or B or C. We then have digit, which has been done for us. That's nice. Unsigned integer, which is a digit or digit and an unsigned integer. Variable, which is a letter followed by a digit, and an assigned statement, which is a variable followed by an operator, followed by a I've so messed this up, my bad. To be fair, I am feeling really sick right now. You might be able to tell. No semicolon. Okay. The definition of variables to change to allow one or two letters. Okay. And 0, 1, or 2 digits. Alright. So we just need to modify what we've got already. So we've got letter, but it's saying one or more, so I'm going to do letter again. And I'm going to do another arrow going around it. So one or more. Where we can have a digit. But if we choose not to have a digit, we need an arrow to go above that as well. I need to tidy this up first, so let's tidy this up. So if we choose not to have a digit, we're doing that. We do need another digit box. So this arrow is basically saying we're having 0 digits. I'm also going to do another arrow, which is going to be here. So we can have 1 digit, or we can have multiple digits, or we can have no digits. But we also need another arrow which skips the letter. Well, hold on. Actually, that looks about right. We've got one letter or two letters, one digit or two digits. Okay, the definition of the assignment statement is altered to say that a syntax has unsigned replaced by real. A real is defined to be, so let's do real first. So a real is at least one digit before a decimal point. So that would be as it's saying at least one, we're going to use an unsigned integer. Decimal point and unsigned integer. Now we're going to have to revise our assignment statement so that it's going to be what we have already, variable dot dot equals variable, then operator, and then real. Pause the video, give this question a go yourself first. In fact, there's several questions. Okay, so we're dealing with RPN, reverse post notation, which is aka known as postfix. It's used in math, where operator follows all operands. It's used in compilation of program code because it's efficient for evaluation. What we normally deal with, which is infix, which is one that I underline here, requires us to have brackets. Brackets makes it harder for a computer to work out what comes first. RPN doesn't use parentheses because each operator has a fixed number of operands, which makes perfect sense. So let's go on with it. Let's deal with the first bracket first, so PQ and then plus. Then the next bracket, PQ, and it's a minus sign. Joining them together is the asterisk. Now we're going to put it into a stack. So these letters represent numbers. So let's just do it here. M is a constant for 10. Tells us here. Q is 2. P, excuse me, 4. 2, 1. Cool. So we've got 10. And if this is anything to go by, so we've got 10, sorry, this even, anything to go by, we've got 10. We've then got Q, which is going to be 2. So we've done these two. We then divide them together. 10 divided by 2 gives us 5, so that's going to be there. We then push P onto our stack, so we're going to have 5, and then we're going to have 4. We could do another one here, which is fine, so we could do 5, 4, 2, or I can do 2 here. Makes a difference. So I've done this. We're going to add these together, but we're only going to add together the last 2. So we're going to still have 5, but it's 4 plus 2, which equals 6. So it's the top of the stack and the one below it, which we add together. So we've now got in our stack 5, 6, and we're going to add 1. we're now going to perform an operation where it's going to be a minus sign. So 6 minus 1, which equals 5. So this is our top of stack. This is what we had in first. And the last thing we do is multiply 5 times 5, which will give us 25. Now what we're going to do is convert this back into infix. So P plus Q. I'm going to put a bracket around it. That's easy enough. Times M. Or multiply M. R, P, minus sign. So we've done these. So the last thing we have is a minus here, which basically separates that. But we need another bracket around here and another bracket around M. And there you go. The final question for this, explain how RPN is used by an interpreter to evaluate expressions evaluated left to right, always. Each operator uses 2 previous values on stack we push new values onto stack and pop when performing calculations. Pause the video, give this a go yourself first. Okay, let's rock and roll. A, B plus. I'm then going to do C, D minus, and then we've got a multiply. This one's a bit harder. So it's going to be A minus. And then we're going to deal with B. So we've got literally I divide next 4. We then have a multiply. I'm now going to do the brackets here, which is going to be CD minus, and then the final thing is divide. Now let's push these onto the stack. So we've got 2, 1, 4, 3. Okay, so we've got 2, 1 in this one, 2, 1, 4. In this one, we've got the plus, so it's going to be 2, 4 plus 1 is 5. In this one, so let me just cross out what I've done so I'm not going to confuse myself. In this one, we're going to have 2, 5, 3. In the next one, 2, and then 2, 5, take away 3 is 2. And the final one, 2 times 2 is 4. Now let's put this back into index. Okay, so we're going to have x multiply, and then we're going to have w, which then we're going to have plus, then we're going to have z. So I've done that. Then we're going to have minus, y. And you would argue you would have that in brackets. And the reason why I've got the brackets is because of the order of precedence, basically. The multiply being first. Okay, one advantage of using RPN? Well, no need for rules of precedence. No need for brackets. Always evaluates left to right in terms of operators. Pause the video, give this a go yourself first. Okay, so this is really easy. I'm going to do both of these questions at the same time. So I'm going to work from left to right. So 8, 5, 2. If element is number, we push onto stack. You know what? I'm going to keep these as separate ones. 8, 8, 5, 8, 5, 2. Great. If element is operator, we pop top of stack and second number to perform operation on said values. So we've got a minus 8, 5 minus 2 is 3. So we've just done that, we popped. And we're going to push results onto stack. That number 3 is our result. So we now got 8 times 3, which is 24. So we've got 24, so we've done these 30, 24, 32, 30, 24, 32, 3, 24, 30, I've just lost track, 3 times 2 is 6, 24, 6, well, 30 divided by 6 even is 5. And minus sign, so 24 minus 5 is 19. So, end once last element in expression has been dealt with. There you go. That's both his questions in one go. Excuse me.